Hello everyone, and welcome back to Total Organic Chemistry. This video, I'll be taking a look at the hydration of alkenes, so adding a molecule of water across that double bond. We'll look at reactions to hydrate that alkene in a Markovnikov and anti-Markovnikov fashion. So by the end of this video, the questions that you should be able to answer for yourself are: how do I hydrate an alkene in acidic conditions? How can I use an oxymercuration reaction to avoid carbocation rearrangements? And finally, how can I use hydroboration to hydrate an alkene in an anti-Markovnikov fashion? If you'd like some review on the properties of alkenes or some of the other reactions that they undergo, please go ahead and subscribe, and also take a look at my previous videos on that. Let's start off with some reactions to hydrate an alkene in a Markovnikov fashion. And remember, Markovnikov means adding the OH to the more substituted center. So if we start with a very simple alkene, propene, and treat it with a dilute solution of sulfuric acid in water, we will get this product, where the alkene has been hydroxylated, so we get this hydroxyl group, the OH group, at the Markovnikov position, so the more substituted carbon. So what is the mechanism for this reaction? Well, we start with our propene, and because we have sulfuric acid in solution, we'll have some sort of H+ floating around. And again, we know that this H+ is never by itself, it's always bonded to something else in solution. In this case, we could have also written hydronium, H3O+, and the pi bond will attack the proton here, giving us the more stable secondary carbocation. And then because we have a lot of water floating around, that water will be nucleophilic, and it will capture the carbocation to give us this protonated alcohol here. And then finally we can draw one of these bonds to hydrogen, coming back towards the oxygen, to regenerate the H+ catalyst and give us the final product, isopropyl alcohol. And if you remember from the reactions of alcohols, if we subject an alcohol to a mixture of concentrated sulfuric acid and really heat the reaction up, we can turn that alcohol back into the alkene. So this is really an equilibrium process, where we can push the equilibrium to the alcohol side by using lots of water in the reaction and relatively low temperature, and we can also push the equilibrium to the alkene by using concentrated sulfuric acid and lots of heat. We could imagine another reaction where we're taking this substituted alkene and treating it with the same conditions, dilute sulfuric acid in water. And at first you might imagine this product, where we've added the OH to the Markovnikov position, so the more substituted carbon. However, you might also notice that because we're forming a carbocation in this reaction, this carbocation can undergo a rearrangement to give the more stable tertiary carbocation that is adjacent to this carbon, and that will give us this product here, the tertiary alcohol, where we've undergone a hydride shift. So if we really want the secondary alcohol, how can we avoid this carbocation rearrangement? Well, we can take the same alkene, and instead of treating it with aqueous sulfuric acid, we treat it first with mercury 2 acetate, so I'll write HgOAc2, where OAc is just an abbreviation for the acetate group. And this is done in usually water as a solvent. And then we follow this up with a reduction step, where we use sodium borohydride, sodium hydroxide, and water. And this will in fact give us the non-rearranged product, where we have the OH group on the secondary carbon. So this reaction is called Oxymercuration-demercuration, where the oxymercuration happens in the first step, and then the second reductive step demercurates our intermediate to give us the final alcohol product. Let's look at the mechanism. So as always, we start with our alkene, and then we can also draw our mercury 2 acetate, where we have this mercury atom in the middle, and it is bonded to each of these oxygens from the acetate groups. And mercury, like many metals, is Lewis acidic, so it can accept the pair of electrons from the pi bond in the alkene. So we'll have those electrons swinging over to attack the mercury, and one of these bonds to the oxygen will swing over actually to attack the other carbon of the alkene. So what this will produce is an intermediate where we have a 3-membered ring, and mercury in this case is going to have a positive formal charge and is still bonded to one of those acetate groups. And if you've watched my video on the halogenation of alkenes, this intermediate should look very familiar to you with the 3-membered ring and the positive formal charge on the heteroatom, and this is also similar to an epoxide ring opening catalyzed by acid. And we remember from those epoxide ring opening reactions that our nucleophile, in this case it's going to be water, will attack from the more substituted carbon, because that more substituted carbon will have somewhat of a carbocation character. So we'll have the water attacking that carbon, and then this pair of electrons in the bond to mercury will swing up to the mercury, giving us this next intermediate here, where we have the protonated alcohol, as well as the mercury group on the adjacent carbon. Next we can draw one of the bonds to hydrogen, just swinging down to the oxygen, and losing a proton in the process, to give us this next compound with the OH group, as well as the mercury group on the vicinal carbon. Finally, in our step with the reductive workup, we'll have the borohydride ion, so that's the BH4- ion from the sodium borohydride, and one of those bonds to hydrogen will swing over to attack this electrophilic carbon here, and then the bond to mercury will come up to the mercury to give us the final alcohol product, where we have no rearrangements and we still have the alcohol on that secondary carbon, the Markovnikov product. What if we wanted to synthesize an anti-Markovnikov alcohol? So if we look at propene again, and once again treating it with our sulfuric acid and water, we'll form isopropyl alcohol, where the OH has bonded to the secondary carbon, and remember this is our Markovnikov product. What if we wanted that OH to be on the primary carbon instead? Well, in that case, we could start with our alkene, and again do a two-step synthesis, where the first step is treating it with borane tetrahydrofuran, and I can draw that here, where we have the tetrahydrofuran ring, and then bonded to that oxygen will be the boron of the borane species. Our workup step will be using hydrogen peroxide, H2O2, in basic solution, so using probably NaOH and H2O. And this will give us the anti-Markovnikov alcohol, so instead of isopropyl alcohol, we now have N-propyl alcohol. And this is called the hydroboration-oxidation reaction, where our first step is the hydroboration, and our workup is the oxidation to give us the final product. As always, let's look at the mechanism. So we start with our propene, and I will draw the borane here without the THF complex, so just the BH3 conveys the mechanism pretty well. And because this boron has only a sextet, remember boron is electron deficient in these cases, it will accept the pair of electrons from the pi bond, and at the same time in a concerted step, the bond to hydrogen will swing over to bond to the other carbon of the alkene. And that will give us the following intermediate, where we have the BH2 group on the primary carbon, and the hydrogen from the borane has bonded to the adjacent carbon. Two things to note about this is that we have the boron bonded to the less sterically hindered carbon, so in this case it's not about carbocation stability, but rather about steric hindrance. So the boron will now be bonded to the less substituted carbon in the alkene, which will be the less sterically hindered one. The other thing to take note of is that this is syn addition of BH3 across the alkene bond. So what that means is that the BH2 group and the hydrogen will be on the same side of the alkene, and we'll look at the consequences of that in a little bit. The next step might be a little different from what you've encountered so far in organic chemistry. Instead of using additional molecules of BH3 to add to more alkenes, we'll use this adduct that we have with the BH2 group and use that in the same mechanism to additional molecules of the propene starting material. So I won't draw those out, but what we eventually get at the end of that process is this compound, where we have the boron center and the three alkyl groups attached to it. So we have the three propyl groups coming from three molecules of alkene, and those are all bonded to the central boron. Then, in our workup step, we have some basic hydrogen peroxide. So what we'll do is we have this nucleophile, the hydroperoxyl anion, so OOH-, and this oxygen here is slightly nucleophilic, so it can attack that boron, giving us this next intermediate here, where the boron now has a minus formal charge, with again the three propyl groups attached to it, as well as the hydroperoxyl group. Then we get an interesting rearrangement reaction, where one of these propyl groups bonded to the boron will swing over to attack the oxygen bonded to the same boron. At the same time, this bond to the other oxygen atom will come off to produce an OH-, as well as our next intermediate, where we have again just the boron center, 2 propyl groups, as well as a propoxy group. Then if you can see a pattern approaching, we do the same thing 2 more times. So we'll finally end up with this boron molecule, where the boron now has 3 propoxy groups instead of just propyl groups. Finally, in our very last step, we will hydrolyze this molecule to give us 3 equivalents of the propyl alcohol product. So that might be one of the more difficult mechanisms you've encountered in organic chemistry so far, but I think it's very interesting to understand and to see where these molecules actually come from. I want to finish up this video by just looking at another example of this hydroboration-oxidation reaction. We can look at this substituted cyclopentene and treat it with our same hydroboration-oxidation conditions. So step 1 is borane in THF, and step 2 is our workup with hydrogen peroxide, sodium hydroxide, and water. So what will our product be from here? Well, we know we'll still have the 5-membered ring with that methyl group, we haven't changed anything about that, but we have broken the double bond, and we know that with hydroboration we're going to add the hydroxyl group in an anti-Markovnikov fashion. So again, that means to the less substituted carbon of the alkene. So that means I can draw the hydroxyl group on this right-hand carbon pointing out of the page towards us. The other thing we talked about is that the BH3 in the first step adds syn to the alkene. So what that means is that the hydrogen atom from the BH3 molecule will be added on the same side as that hydroxyl group. So I can draw this H, again coming out of the page, on the left-hand carbon of the alkene. So now that we know that stereochemistry, we can fill in the methyl group here, going into the page, as well as the hydrogen on the right-hand carbon going into the page. So notice how the hydroxyl group and methyl groups are trans in this case, because we've added the molecule of H2O overall syn to the alkene, so on the same side. So I hope this video helped you understand the addition of hydroxyl groups to alkenes, or the hydration of alkenes. If you enjoyed this video, please like and subscribe to my channel. Like me on Facebook, and check out my website on the screen. If you're willing and able, please consider donating to my Patreon page, which really helps me to continue creating all of this content for all of you. Thanks for watching.